Hello everybody. In this video we're going to talk about how to compute volume from a digital elevation model using raster statistics. So a digital elevation model is a grid of numbers where each pixel in the grid represents elevation, right? That's height above ground. So the cool thing about a digital elevation model is we actually have a z dimension. We have an x, a y, and a z dimension where that z is elevation. So it actually allows us to compute the volume of material beneath any given surface that we might want. And the best way to do this is to essentially take your DEM, which is already divided up into pixels, right? And if it's projected, these are square pixels. So all you need to do is add up the volume within each of the pixels underneath your object, and then you have the total volume underneath your surface. So it's essentially an integral, or something like a Riemann sum. So in our video today, we're going to look at Mount Shasta, which we've been working on. It's a volcano, it's conical, and we might want to ask the question, how much magma is within Mount Shasta? So what we're going to do is we're going to extract the digital elevation model above the 1,880 meter contour, right? We've actually already done that. We're gonna clip out this part of the DEM that's above that, and then we're gonna compute the volume. And the way we're gonna do that is we're gonna first determine the mean pixel height. So we're going to figure out the mean elevation of all the pixels that make up Mount Shasta, and imagine each one as a column. Then we're gonna subtract off the base elevation here. So the mean pixel height will be the height of a pixel minus the base elevation of 1880, and then we'll average all the pixels to get the mean pixel height. So it's not the mean elevation, right? Then we will get the total area of all those pixels, and that's fairly straightforward. It's just the area of each pixel, which is pixel length times pixel width. Okay, that's the area of a pixel, summed up across our entire area of interest. And then from that, volume is simply the mean pixel height times the total area. So it's this thing times this thing. All right, and we're going to do this using raster statistics. So here is our digital elevation model of Mount Shasta. And here is the masked raster. And this was created by getting the 1,880 meter contour line, and then using a mask, creating a masked raster where we only have values inside the 1,880 meter contour, right? So there's that masked raster. Notice if I clip inside the raster, we get an elevation value for that pixel. If I clip outside the masked raster, we get no data for those pixels. Okay, and I've also got a spreadsheet where we can keep track of our calculations. So the things that we just talked about are average height, total area, and total volume. So we just talked about how that's what we need to do this calculation. In addition, we're going to need to get the pixel area, so the area of each pixel. And we need to estimate the number of pixels. And it turns out this is a little bit confusing because it's a little bit hard to actually get this number from a masked raster. You can do it using zonal statistics, but if you have projection issues in any of your data, you may need to use a workaround that I'm going to show you here today. All right, so let's start populating this spreadsheet with some of this data. All right, so first thing I'm going to do is right-click on the masked layer, go into Properties and Information, and we can see a lot of the statistics right through here, including the mean elevation. But notice the statistics are approximate. So to fix that and make them exact statistics, we're actually going to go into Symbology, go into Single Band Grayscale, Min-Max, and we're going to, instead of using estimated accuracy, we're going to use actual accuracy and hit Apply. So that's going to actually compute the exact statistics. Notice when we go back, the statistics are now a little bit different and they're exact. All right, so first thing we need is the mean elevation. That's 2371 meters. Okay, and so we're going to put that under average height. So average height is given by the average elevation minus the base elevation. Remember that from our intro. So average height of the pixels is 491. All right, what about pixel area? We can get that by looking down here at pixel size, 2.84 by 2.84, and our unit is meters up here, okay? So our pixel size is 2.84 times 2.84, 8.1 meters squared per pixel. Great. So now here's the tricky part. How are we going to get the number of pixels? The problem is that if ordinarily with a square raster, you could just do this width times height right here. But if you do this, this is actually going to give you the number of pixels in the entire original raster, not the number of pixels within the mask. So to get the number of pixels within the mask, you could use zonal statistics, but if you have any kind of projection issues, this won't work, and we're going to in the Mars lab. So we're going to do a little bit of a workaround. We're going to use raster layer statistics here, and we'll just put in our raster layer as our masked, okay, masked DEM, and we'll just save them to a temporary file. We'll hit run, and I think that happens instantly. And then here it gives us a file path to find those statistics. It'll open them up in a web browser. And so here they are: minimum, maximum, range, sum, mean, standard deviation, and so on. And so what we can actually use is this sum, because we know it probably did add up all the pixels in the raster, inside and outside the mask, but since everything outside the mask is no data, we can be confident that this sum is really only a sum of the pixels within the mask, okay? So I'm going to put that right in here into sum, and then I'm going to recognize this kind of simple fact that the number of pixels, right, must equal the sum divided by the average height. Another way of saying that is the average of something equals the sum divided by the number of pixels. So we can compute the number of pixels that way. Then we can get total area by multiplying the number of pixels times the pixel area. And then we can get total volume by multiplying the total area times the average height. And that's going to come in meters cubed. So the volume of Mount Shasta is 5.4 times 10 to the 11 meter cubed. Hope this helps. I apologize for the confusing workaround about how we got the number of pixels. Let me know if you have questions.